Confidentiality and verifiability are crucial for AI and sensitive data, particularly in fields such as digital marketing, healthcare, finance, and secure collaboration between companies. As part of its solution, Super Protocol has built its own certification system, ensuring secure and verifiable computation in a confidential environment. Like a certificate authority for SSL, it certifies the entire trusted setup before any execution begins, automatically, inside trusted execution environments or TEEs. This allows developers, data owners, and users to verify the integrity of their applications and data, ensuring only the expected code runs and blocking any mismatches before the process starts. Super Protocol Certification System handles all the complexities of remote attestation in the background. The system is TEE agnostic and supports multiple technologies, including Intel TDX, AMD SEV SMP, and NVIDIA confidential computing. Besides, the whole system is open source, ensuring transparency, auditability, and trust. The certification system architecture may look simple on the surface, but it's grounded in sophisticated mechanisms. At its core is a hierarchy of certification authorities operating within trusted execution environments. At the highest hierarchical level is the root certification authority. During the system initialization, the root CA generates a self-signed certificate embedding an Intel SGX attestation quote. Subroot certification authorities are located at the next hierarchical level. These submit their quotes and public keys to the root CA and request certificates. The root CA verifies these incoming requests and then issues and signs certificates for the subroot CAs. Subroot certification authorities function as a certification service, combining the functions of an attestation verification service with a certificate authority. The certification service receives requests and issues certificates based on attestation evidence, verifying that the requester operates in a confidential environment. Let's see how Super Protocol uses its certification system. In the classic remote attestation scheme, you launch an environment and then confirm that it matches your expectations. Super Protocol has gone further. It verifies the TEE integrity before bringing in the workload components from different owners and executing them. This process involves Trusted Loader, an application responsible for loading the workload inside the TEE, requesting certificates, and orchestrating the job. Trusted Loader will eventually be open source, just like all other Super Protocol components. It operates inside an Ubuntu confidential virtual machine that will execute the workload. The CVM's image is publicly available in the Super Protocol SPVM repository. When the TEE is created and the Trusted Loader is launched, it provides the attestation measurement to the subroot CA and receives a certificate that includes MR Enclave and MR Signer, confirming the Trusted Loader indeed works inside a TEE. Then, the Trusted Loader generates a TEE confirmation block, or TCB. It contains the certificate and various information about the confidential VM, including its hash. Trusted Loader signs and publishes this TCB on the blockchain, BNB chain. This allows the workload owners to validate the machine. If the verification is valid, the workload is sent to the TEE. During the order execution, the Trusted Loader validates the workload integrity and generates workload info that includes the workload components types, sizes, hashes, and other metadata. Then, the Trusted Loader sends a certificate request to a subroot CA. The generated order certificate includes MR Enclave, MR Signer, and the workload info hash. After validating the components, Trusted Loader makes the certificate available to the workload through the orders file system. Trusted Loader also creates a report containing the full certificate chain, from the root CA to the order certificate, as well as the workload info. This report is published on the blockchain right before the workload execution. Now, let's put it into practice. Super Protocol created the example signer, a set of scripts you can use as a demonstration or example. Some of these scripts are for local testing, while others are for deploying a demo application in a confidential environment and validating it. You can find the example signer in the Super Protocol Solutions repository on GitHub. The repository also contains a README file with step-by-step instructions. Let's start with the local testing and emulate what happens inside a confidential virtual machine. We clone the repository, navigate to the example signer, and create two directories, certs and output. In a real case scenario, these will be SP certs and SP output. SP certs is for the certificates, private key, and workload info. And SP output is for the execution results. Both directories are available to the workload during execution. First, we execute the generate certs script. It creates a self-signed certificate, certificate chain, and a private key and places them in the certs directory. Next, we run sign data sh. This script plays the role of the workload. It copies the certificate and the certificate chain from certs to the output. Then, it creates a JSON file with crypto exchange rates using the CoinGecko API. Finally, the script signs the data using the certificate's private key. Let's verify the certificate using the verify signature script. The report shows that the certificate chain was successfully verified. Note that we used a self-signed certificate. It is also both the root and the end certificate because we are testing locally. In a real case scenario, there would be a proper certificate chain with 3 certificates. Let's see how it looks. To do so, we will execute our demo application, the sign data script, in a confidential environment on Super Protocol using the Super Protocol CLI tool called SPCTL. For this demonstration, we have already installed and configured SPCTL in the example signer directory. We also deleted the certs and output directories as we do not need them anymore. In the example signer directory, you can find the Docker file with a configuration for building the application container. Now zip the image into a tar.gz archive. Let's calculate the archive hash to verify it later and ensure we're working with unaltered data. Before placing an order to execute the application on Super Protocol, we should encrypt and upload the archive to distributed storage using SPCTL. When the upload is complete, SPCTL creates a resource JSON file with information on how to access the uploaded archive. It contains the file name, hash, storage, bucket name, access token, encryption key, and other information. Now we can create an order to execute the uploaded application. Here is the ID of the order. A couple of minutes later, the execution is done, and we download the result. It is archived, so we unpack it. The output directory contains the order certificate, the certificate chain, the signature, and the JSON report file. To verify the certificates and the signature, we can use the verify signature script. Note that we set the environment variable, certsdir, to point the script at the output directory that contains the certificates. Let's review the report from the beginning. The certificate chain contains 3 certificates, and it's valid. The first certificate in the report is the N certificate, or the order certificate. Here is the ID of our order. CA false means this certificate cannot be used to issue further certificates. You can also see here that the order was executed inside an Intel TDX trusted execution environment. If we were executing the order on an AMD SEV SNP machine, the report would reflect that. Next, there is an intermediate certificate, the subroot certificate. CA true means the subroot certificate authority can issue certificates using this certificate. The third certificate is the self-signed root certificate. At the end of the report, there is a confirmation that the signature was verified. Here is our signed data. Finally, let's review the order report that Trusted Loader published on the blockchain. It includes the same certificate chain we just saw in the verify signature script. SPCTL validates the certificates, as well as MR enclave for every certificate in it. The report also includes the runtime info array, which contains the hash of the solution. The Trusted Loader generated this hash based on the solution executed on the confidential virtual machine. It indeed matches the hash of the archive with our demo application. To summarize, the key benefits of the Super Protocol certification system are data integrity, proof of computation, automatic checks, no need for TEE expert knowledge. For more details on attestation, visit the confidential computing section at superprotocol.com or check out the Super Protocol documentation. Super Protocol, making attestation simple.